This is a softrock. It's a little bit modified. You can read about that on my homepage, at least a little bit about it. This softrock is connected to a signal generator now, here, and I'm going to install it in Linrad and also show how to calibrate it. The computer, this one, with the USB input here, is running Ubuntu 12.04. All libraries are installed, and I'm not going to talk about hardware related parts of the software. I mean the drive routines. They are installed, and that is a simple process that I have described on other places. Now I'm going to the setup of the processing parameters and also a little bit more about normal user. So we need a terminal to start with, and to be able to see it better I can zoom in a step. Here we are. First I set user root. And then I go to the place where the Linrad installation is sitting. CD, and here we have xlinrad 64, but no parameter files. I have removed them, all of them. So when we start, the setup screen will appear. And now I go for normal mode. That's S. Reason is it was set up. There were no other options in the beginning. So, and I make fairly big letters on the screen. That will be 2. And I use these libraries because they run a little bit faster. It doesn't matter on this fast machine. I don't need to block any CPUs. They wouldn't be blocked anyway because the data rate is very small for this softrock. It only runs on 96 kilohertz. Screen size 1024 by 768. That's kind of standard size. And so I can save the parameters we set so far by pressing W. And then to set up input and output, the command is U. And here you see red lines saying there is no input and no output. So first select the input A and sound card, that's A. Do not use, put audio, that's no here. And then the M audio delta 44, that's 3. And maximum speed, that's 11. And this is a 4-channel sound card, but the softrock has only I and Q for 1 radio channel, so I say 2 here. And there is no skew between the samples, so I don't have to do any time shift. That means 0. And the softrock has SI 570 for controlling the frequency. That's the reason why I'm running as root, because there is something with permissions for the USB that I don't know how to set, and it's far more convenient to always run as root, in my opinion. So I always do that. although I'm well aware it is not recommended, particularly not in the graphical environment. So I select 3. And we need some output. That's B. And not put audio here either. Sorry, I pressed the wrong button. So it doesn't matter. We can take the number 1 and latency factor 2. And don't forget to save what we did. So I press W to save. And now we can go to the SSB mode, that is D. And we are prompted to the parameter selection because there are no parameter files yet. And I take the default by just pressing enter on all these menus. And here we are. The frequency is 1.8 megahertz, but the signal is on 14. So I enter 14 here. 14 megahertz. And like that. And you can see the signal here and the mirror image there. It is nearly 40 decibel image rejection. Reasonable, but not very good. There is one thing to investigate first, and that is the signal levels. If I press A, I can see that the signals are now 16 decibels below saturation. I move the signals closer to the center. Maybe like that. And increase the signal level. And it's 1 dB per step. And you see it's saturating. This is saturation in the soft rock, because there is still 13 decibel headroom in the sound card. So we need to increase the gain of the sound card. So to increase the signal levels, we need to use a mixer program. On multimedia, and in this system it's called just mixer. Here, and to make it easier, magnify vertically, and then I can turn the controls up, and you see the mirror rejection becomes very bad because I bring up one channel but not the other, and I bring up the other channel as well, and here it looks good. So now the signal levels are the same. I can press Z. Okay, I have to get focus here first and then press Z to clear the amplitude margin indicator. It's 1.07 dB on the I channel and 0.82 dB on the Q channel. So this is fine. If I now increase the signal level, you can see that it saturates. It saturates differently now than it did before, because this is saturation in the sound card. And you can see that the amplitude margin is 0 here. So I go back like that, and maybe one more, press Z again. So we have 2 dB margin to saturation. Now it's time to calibrate the image rejection. So that is X and C for calibrate, and A for the phase and amplitude between I and Q, A. Each segment is 3 kilohertz. That means 96 divided by 32. So I tell the signal generator frequency increment set 3 kilohertz. Then I can press the step button, step upwards, and you see it comes red and then green, red, green, red. So and then at the other side, now we have collected the phase and amplitude relation between the mirror and the signal in 32 points. The next step is to press U to compute the calibration function from the collected data. U, and I press plus to look a little bit at it. Looks reasonable. Press enter, and we can see the mirror image is now here. Now go up in frequency, and you see the mirror image is fairly low here. So this was successful, and you see I am pressing quickly because I'm not going to use this collected data because the result was already good. So just press S to save the data we are using now. S, and then X, and X again, sorry, D. Here we are in SSB mode, and we have now a very good image suppression. So you can see the keying clicks from stepping the frequency is far stronger than the mirror image, which is at a little bit above 40, while the signal is a little bit above 120. That's about 80 decibels. That's about what you get doing it this standard way. The next step is to calibrate the frequency response. The Softrock operates on 14 MHz. That's a low frequency, so I can use a simple function generator like this one. As you can see, the background noise isn't perfect on this system. That's because this computer is very noisy. So even though this is a modified Delta 44, it picks up interference from the computer. But for these things I'm doing here, it doesn't matter. Now I'm going to start the calibration for the frequency response. So I switch on the function generator. And you see we get some wideband signal. Now I turn up the amplitude. And here you can see something happens at the center here. This gives a lot of signal, and that is more than the mixer of the Softrock can manage. So I have to turn the amplitude down to somewhere. So for the flat noise to be maybe 5 dB or something below the maximum value we had. This could be a reasonable level to do the pulse calibration. Before doing the calibration, I will make the current frequency response more visible. And now you can see we have from here to here about half a decibel or maybe a little more. To see this better, I will increase the averaging, and to do that I have to increase the storage time for the transforms. X, P for parameters. First FFT storage time, let's make it 10 seconds. And then I can increase here and make something really big. And now we can see that it's from here to here. What is it? 0.7 decibels or something like that. So, and a faster waterfall. And some more gain on the waterfall. And I change the 0 point. I can right click in this box and then we get it bluish. Now, so this is, you can see that it is a little bit less blue here than here, but the gain in the waterfall is just 1 now, so it's not very sensitive. To do the calibration, I press X and then C, and it's the total amplitude and phase, so it is B. And here are the pulses. And to show what the problem was when the pulses were too strong, I turn up the pulse amplitude. And you can see from each pulse there is something. And we can see here it's a DC voltage that extends for a long time after the pulse. That's an artifact from having saturated the mixer, or maybe the input, the amplifier after the mixer. I don't know exactly, but this is too much signal. So I go back to here. The white curve is the power logarithmic scale, and here magenta and green is INQ. When I'm happy with these pulses, I can change frequency. We have now 382 Hertz. The function generator is set at 191, and it's a square wave, so each transition on the square wave gives a pulse, so we have double the pulse repetition frequency here. So when satisfied, I press enter. And now Linrad is collecting the Fourier transform of the pulses, the average Fourier transform. The green curve is the second derivative of the phase, and the magenta is the amplitude. And this runs fairly rapidly. We have now about 10,000 pulses already, and that's enough, even though the signal-to-noise ratio of these pulses is very poor. So the next step is to compute the new corrections in RAM memory and not save it yet. That's U. The green curve is the second derivative of the phase. The white curve is the frequency response we want to have. And the yellow curve is the difference between what we have now and what we want to have. So the yellow curve differs by about 0.7 dB from here to here, as we saw previously. So I just now accept the defaults, and that's Y. And we can look. Now the second derivative of the phase is flat, and the amplitude is also nearly flat. It's not perfect. There is something wrong here near the center, and we know why. It has to do with the size of the pulses. But this is good enough. I just say save to disk from RAM. That is S. And exit and go back to SSB without change. And here you can see now the waterfall has the same color the entire way. The gain through the processing has changed a little, but you can see now it is very flat. We can try to average a little bit more to see whether it becomes even a little bit flatter. So this looks good. Now that calibration is complete, I can enable the second FFT and run the noise blanker. That's X, and then parameters. Enable the second FFT. That's 1 here, and I don't change anything else. So we got a new window here. I want to look at the S meter, so we move it for you. And I want it as a graph. And I want to have a look at the oscilloscope traces. So I have to make that area of the screen free. So first, click here somewhere in the noise and look at the decibel scale. The white is peak power and the yellow is RMS power. Enable the noise blanker. That is the yellow for the dumb blanker. And 10%, that's far too much to remove by the dumb blanker at this wide bandwidth. So I have to move the threshold upwards, maybe 3%. And we lose some performance by doing that. Then I can enable the smart blanker here. And it doesn't make any difference. remove the dump blanker. Now it's only the smart blanker. And the difference between the smart blanker and the dump blanker is that the dump blanker will cut holes in those signals that are present, and those cutting of holes produces keying clicks that spread over the entire passband. The smart blanker is subtracting the appropriate curve form, and it doesn't have those artifacts with it. Now you can see the red points here. Those are excluded from the signal that goes into the noise blanker. I can change the amount of points that become red, and you see it doesn't make any difference here. And if I switch on the dump blanker again to have both blankers, it doesn't matter. Look at the waterfall. I press the right button here to auto adjust the color scale. The question is, how good is the blanker? And I can switch off the function generator like that, and you can see the noise goes down tremendously. And one might think that this is because the blanker isn't so good, but that's not the reason. It's just a lousy function generator, and I will demonstrate that by becoming an expert on Linrad. But before, I will show a little bit what you can do as an ordinary user. X, and I, that is sound card test mode. Here it's just an oscilloscope. I can make a pause, that is P, and you can see pulses. One pulse, one pulse, one pulse, and one pulse. And then R for resume, and plus to increase the gain, like that. And now when I switch off the pulse generator, look what happens. The function generator is noisy. I switch it on again and make a pause in the oscilloscope by P. Here you can see that the noise is about the same in the positive and in the negative half period of the square wave. That's because I have the normal square wave output. It's an ordinary amplifier of some kind. To investigate how the blanker really works, I need a better pulse generator. This function generator is good enough to get a reasonable calibration with some functionality of the noise blanker. Another video will show what it looks when one uses a better pulse source.